from Leiden. We're going to start on time. We're going to have the presentations first, then the judges' questions are going to follow, and then if we still have time, we're going to open it to questions from the public. We'll call on people. Okay, so we'll start with the energetic orange team from Leiden. Welcome to the stage, Team Leiden.
Thank you. Good morning, everyone. Well, let me start by highlighting a disaster many people are not aware about. A deadly disease is spreading across the globe, and as it spreads, more and more people are hospitalized or die. Doctors are baffled on how to treat this infection, as it's being caused by a bacterial infection which has become resistant to all our current antibiotics. And by the end of a single year, 10 million people around the globe have died, and this number is only expected to grow worse in coming years. Now, fortunately, we still have 30 years to avert this disaster from becoming a reality, because these figures are based on a recent paper in Nature Microbiology which estimates 10 million annual antimicrobial resistant related deaths by the year 2050. And although 2050 might seem like a long way off, if we want to have any hope at stopping this crisis, the time to act is today. Now, one of the solutions might seem simple. We want to discover new antimicrobials to treat bacterial infections which have become resistant to current ones. But it's precisely here where one of the problems lies. Since the 1950s, the discovery of antibiotics has been declining. And in the past 3 decades, no new classes of antibiotics have been discovered. Am I all okay? I'll just do this thing. So that's precisely the problem. And that's why we, iGEM-Leiden, have decided to tackle this problem with our project, which we call 50 Shades of Stress, which is a colorful screening platform for detecting bacterial cell stress. And this platform aims to rejuvenate antibiotic discovery research. And we created this project by talking to many experts in the field of antibiotic discovery. And using these dialogues, we determined 2 key missed opportunities in current research. Well, first of all, we noticed that it currently takes a very long time to determine the mode of action of compounds discovered in the lab. So what we aim to do is to shorten the discovery time of this mode of action and thereby shorten drug discovery timelines and have a faster introduction to the market of novel drugs. And additionally, we aim to look beyond lethal substances, which is what all current research focuses on, and start looking at stressful compounds as well, which are capable at damaging bacteria without killing them directly. Because we believe these stressful compounds can be used in synergy therapy, in which a stressful compound is combined with an antibiotic to increase its effectiveness, and thereby allow the antibiotic to once again kill resistant bacteria. So our goal was to create a system which can detect stressful and both lethal compounds while also determining their mode of action. And for this, we've looked at the endogenous stress response of our model organism E. coli. For example, should DNA damage occur in E. coli, certain promoters will become activated and start upregulating their associated genes, which could, for example, be repair proteins of the DNA. An example of such a gene and promoter combination is the SOX-S gene in promoter. So what we've done is we've taken this promoter and put it in front of a GFP fluorescent tag, so that next time the bacterial cell experiences stress, not only will it start repairing its DNA, but it will also start producing a fluorescent signal in the form of GFP, thereby visualizing cell stress. So we've created this construct and tested it against various concentrations of nalidixic acid, which is an antibiotic known to cause DNA damage. And what we see is that the higher concentrations of nalidixic acid we add, the higher the GFP expression of our construct becomes, until we add a lethal dose, killing the bacteria and stopping GFP production. And what we see is that our system is able to visualize up to 20 times lower amounts of nalidixic acid-induced stress in this cell line compared to current techniques, which are only able to visualize the lethal dose, thereby proving our system can visualize bacterial cell stress. Now, of course, our goal is not just to visualize bacterial cell stress, but we also want to know the mode of action. And for that, we need to know that this SOX-S upregulation is DNA damage specific. So to test this, we added a compound library of antibiotics, each targeting different cellular pathways, and determined to which antibiotics our SOX-S promoter became upregulated. And what we see is specific upregulation to nalidixic acid and zeocin, which are both DNA damage-inducing antibiotics, in contrary to all other antibiotics added. So we can see that we are, besides being able to detect stressful substances, we can also determine its mode of action. Now, of course, the next goal is to not just detect DNA damage, but to detect any kind of bacterial cell stress. And that's why we've identified 25 additional promoters, each specific to different hallmark stress pathways of the bacterial cell. And we've once again isolated and characterized each of them and submitted them as basic promoter parts, besides submitting 18 composite parts using our promoters. And again, we've characterized each of these promoters. Here you can see an example of a heat map with our SOX-S promoter, and the higher the red intensity is, the more the promoter has been upregulated. And again, we see that SOX-S becomes upregulated in response to zeaxanthin and nalidixic acid, the DNA damage-inducing antibiotics. But we've now also added some additional stressors to test for, one of them being hydrogen peroxide, which is also known to cause DNA damage. So again, we've tested each of our promoters to our library of stressors, and what we see is a unique pattern for each of our promoters to each of our stressors, thereby showing that our system can be used to detect specific kinds of cellular stress in bacteria. So this is great. We now have a system which we can use to detect cellular stress. But of course, the goal eventually is to create an easy-to-use system, which researchers worldwide can use to look for novel antibiotic synergy therapies with stressful substances. So for this, we again spoke to stakeholders of our project, such as Toxis, a company involved in stress responses in mammalian cells, or academic researchers of various universities and institutions. And what they all told us is that there are 4 key product design objectives we need to be mindful of. First of all, our system will have to be easy to use. Any researcher without experience with a system such as ours should be able to use it, and they should be able to use it in any ML1 lab. Additionally, our system would have to be compatible with current fluorescent detection methods, so that researchers do not have to buy new, expensive equipment to use our kit. Next, it would of course have to comply to genetically modified organism packaging regulations worldwide to allow our GMOs to be shipped to laboratories. And lastly, we've learned that researchers would want to use the system in many different ways, and therefore it would have to both be able to be used in high and low throughput experiments. So based on these requirements, we started designing, and we went through multiple design iterations. Can you still hear me?
Yes.
Oh, okay, great. And finally, we designed our final system. First of all, our system will be integrated into the E. coli genome, thereby creating a stable cell line which is easy to use by researchers. In total, 3 stress promoters will be integrated into each cell line, each coupled to a different fluorescent tag, optimized for the 3 most used wavelengths in current research. In total, we will be using 4 cell lines for a total of 12 stress responses to be detected to allow for full spectrum testing using our system. Now, subsequently, these cell lines will be freeze-dried into wells which already contain powdered minimal medium, thereby allowing for safe storage and transport, and additionally, GMO packaging will be added to allow for shipping worldwide. Now, once testing has to be commenced, strips of 8 wells can be added into 96 well plates, and all that needs to be done by the researcher is the addition of Milicu to dissolve our added minimal medium and thereby revive freeze-dried cells. Next, researchers can add compounds to be tested to the plate, and after a few hours of incubation time, the plate can be inserted into any 96 well plate compatible fluorescence detection device to detect fluorescence and determine which compounds are causing which kind of stress in bacterial cells. And using our system, which we've got 50 SOS, bacterial cell stress detection becomes much easier and researchers can start creating synergy therapies. And now, of course, the big question is probably, does this system work? Can we find novel synergy therapies using our system? So for this, we performed a demonstration screening experiment. For the screening experiment, we started with 20 natural compounds, such as ginger, caffeine, garlic, and vitamin C. First of all, we tested whether any of these compounds were able to inhibit growth or kill bacteria by themselves, and we removed them from our screening experiments to ensure that any compounds we did find were purely stressful and not growth inhibiting or killing bacteria by themselves. So with the substances that remained, we tested them on our 50 SOS screening system, and what we saw was that vitamin C hits for one of our promoters. So, to see whether this apparently stressful substance, vitamin C, could be used in synergy therapy with antibiotics, we combined it with many antibiotics to determine the effect. And the results can be seen here. In this case, we used the antibiotic chloramphenicol, and on the left, you can see the lethal dose of chloramphenicol required to kill bacteria without vitamin C, and on the right, you will be able to see the lethal dose required of chloramphenicol with the addition of vitamin C. And what we saw was that the addition of vitamin C significantly reduced the amount of chloramphenicol needed to kill bacterial cells. And not only did we saw this was the case for chloramphenicol, we saw the same for two other antibiotics, namely ampicillin and nalic acid, which is particularly interesting because each of these antibiotics belong to target distinct cellular pathways in bacteria, showing that this synergistic effect of vitamin C is not target specific. So now that we've proven that our system works, of course the goal is to distribute it worldwide so that every researcher can start looking for stressful substances. So for this we started talking to small startup companies doing similar research to us, and to Luris, which is an advisement company on starting up entrepreneurs. And what we designed was a hybrid business plan, which in short can be summarized with two goals. Namely, firstly, it will aim to develop our kit further and distribute it around the world, and we will use the profits gained by the sales of this kit to do antibiotic development ourselves. So now we have a kit, and we also already have stakeholders who want to buy our kit. But we did notice there were some stakeholders who really liked our system, but thought that our kit was not best suited for them. Namely, some researchers do a different kind of research. For example, the so-called streptomyces overlay, which is a traditional kind of screening used to discover many of the antibiotics we use today. For this kind of screening, instead of testing directly compounds, instead organisms are tested which can potentially secrete antibiotics. For example, in a streptomyces overlay, a colony of streptomyces, seen in grey, is added onto a layer of E. coli, seen in orange. And should these streptomyces be producing an antimicrobial, they will secrete it in the surrounding medium, thereby killing the surrounding bacteria and causing a visual death zone. However, one of the key limitations of this technique is that it's not able to detect stressful substances because, of course, there's no death zone visible. So using our cell lines, we could visualize, firstly, we could visualize the mode of action of lethal compounds, but visual by a stress zone surrounding the death zone, where the concentrations of the antibiotics secreted are not high enough to kill the bacteria, but are high enough to stress them and thereby visualize the kind of stress being experienced. But more interestingly, our cell line could be used to detect stressful substances by visualizing a stress zone, which also shows the mode of action surrounding a colony of streptomyces. Now, to prove this system, we've performed similar experiments with so-called disc diffusions, which are very similar, but instead of using a streptomyces colony, we simply use a disc which have been added into an antibiotic solution, so that we can add the discs directly onto the E. coli layer, which will start diffusing the antibiotic as a sort of proof of concept system. And to determine what parts of the plate would be encountering stress, we designed a model to determine the diffusion constants and how the antibiotic would diffuse to the plate. So you can see our model here, and you can see at the center of the disc, at position 0, the concentration of antibiotic is obviously highest. And what we modeled was that the concentrations dropped sharply. Well, and in our earlier experiments, which I've shown before, we had already determined that a concentration of 0.5 micrograms per milliliter of antibiotic should be stressful to cells and thereby upregulate our promoters. So what we did is we performed a disc diffusion experiment using our GFP cell line, and we took a sample at 20 millimeters where the stress should be experienced according to our model, and we also took a sample at 45 millimeters where we do not expect stress according to our model. And indeed we saw that the sample at 20 millimeters had a high expression of GFP, while the one at 45 millimeters did not, thereby showing that our GFP cell line could be used to enhance traditional screening. But of course, using a GFP cell line is not very efficient if you want to have a visual readout. So therefore we upgraded our cell line from a GFP reporter to a chromoprotein reporter, in this case amylCP, currently provided to the iGEM registry by iGEM-Leiden 2014. And using this cell line, we performed another disc diffusion assay. And what we indeed saw was that surrounding the death halo around the disc, we could also see a colorful stress zone, in this case in gray, and in this case visualizing DNA damage induced by nalic acid through the SOX-S promoter. So what we've now shown is that we both have a kit which can be used in low and high throughput compound screening, and we've developed a cell line which can be used to enhance traditional antibiotic screening. But one big problem still remains, is that although we can find novel antibiotics, this does not prevent bacteria from becoming resistant to them, which is something that has been repeatedly stressed by both representatives of the Dutch government, World Health Organization, and European Union we've talked with. They all said that to slow the spread of resistance, antibiotic use across the globe must improve. And particularly they've stated that currently the general populace often isn't aware enough of the risks of antibiotic resistance and thereby overuses and misuses antibiotics. So we determined in combination with these, conversation with these representatives that the awareness around the world would have to improve. So for this, we designed an open source workshop we called Escape the Resistance, which has the goal of globally improving the use of antibiotics. And we performed this workshop at over 10 events with over 1,000 participants, each time asking for participant feedback and improving on the system, and also asking experts about our workshop and asking them for advice to create the best workshop we could. And we've provided this workshop for open source on our wiki for anyone to use. But to ensure that it is used globally, we've also gifted it to the International Federation of Medical Student Associations, which is spread around the globe, to help us spread awareness of resistance globally. And now, this is the first step to stop resistance, but we also think our system can be used in another way to slow the spread of resistance, namely in a completely novel type of therapy, of combination therapies of stressful substances for which multiple stressful substances are combined to create one lethal cocktail, instead of combining a stressful substance with an existing antibiotic. And the advantage of this could be that these stressful substances will target different cellular pathways in the cell, and thereby, for the cell to become resistant, it will have to have multiple different kinds of mutations in completely different parts of the cell to overcome each type of damage. And this is a concept which has already been proven to work in HIV, cancer and malaria treatments, where it's shown that combination therapies can slow the creation of resistance. So the idea is we combine multiple stressful compounds found with our 50 SOS screening kit, which each individually is not able to kill bacteria, but combined is able to synergistically kill bacteria, thereby creating novel antibiotic therapies. So, to summarize, our system can be used in 3 key ways to enhance antibiotic discovery. First of all, we can shorten antibiotic development by providing an early output of compounds, the way the compound works. We can decrease the quantity of antibiotics required by combining them with stressful substances, and we can combine multiple stressful compounds in novel combination therapy with a decreased chance of resistance. And hereby, we can help safeguard your future. So what we've done for this is we've characterized an extensive promoter repertoire, each added to the iGEM registry, and using these promoters, we've developed our 50 SOS screening kit and our chromoprotein cell lines to be used open source. And we've created an extensive awareness campaign which will continue worldwide to spread global awareness about resistance. And now all that remains is for researchers worldwide to use this system to develop new antibiotics and help safeguard the world. So for now, I would just like to thank a few people and teams who helped bring us to this stage. First of all the teams we collaborated with during the iGEM competition, such as iGEM Bordeaux and UC Davis, who helped us in validating our stress responses. I would like to thank iGEM Rotterdam, who we had the honor of mentoring and we also learned a great deal of. And I would like to thank all the Dutch iGEM teams who visited our Dutch meetup and barbecue. And I would like to thank all the other teams we had fun iGEM community events with. Next, I would like to acknowledge and thank all the people who aided our system, our projects in other ways, such as experimental support, or by providing us with feedback on our system. And of course, I would like to thank all of our sponsors who helped make our project a reality. But lastly, I would like to thank all of you for your attention, and we would love to open discussion with you about our projects. Thanks very much.
Stability of the color readout, both for the fluorescence or for the chromoprotein? For how long is it stable and so on?
Well, I suppose that depends on the protein and how fast it degrades, and the GP is stable for, it's relatively stable for hours to days, I think, and the chromoprotein, once that is produced, it doesn't disappear.
Thanks for your talk, guys. I had a question about your the workshop that you guys are working on. So I know you said that you use feedback from your participants to improve it. Can you describe a bit what kind of feedback you got and how you used that to improve the workshop?
Well, particularly some feedback we got was that sometimes they couldn't understand specific parts or parts were too complicated, and so we improved on them, obviously. But what we also did is we asked at the end and at the beginning what they already know about antibiotic resistance, and at the end what they've learned. And based on that, we also determined whether they actually learned what we wanted them to learn, and based on that, we were also able to improve the workshop.
Amazing project, guys. It seems you put in a lot of work, especially in the outreach. You had so many collaborators. I'm really happy for that. But in the lab work, I wanted to wonder if you tested any combinations as you promised of the therapy, whether it increased the stress zones of the colonies or not. And like, did you test any combinations?
Well, due to time constraints, we did not have the ability to test the actual combination therapies. But it has been proven to work in other diseases, so we don't believe that wouldn't work in this case.
The main goal with our project was particularly creating the system for which other researchers can use to hopefully discover novel combination therapies.
So for the plates that you made as a potential product, were you ever able to prototype them fully and give them to other labs to test maybe, or how far has that product development come?
Well, we haven't been able to create the kit yet. So no, we haven't been able to do that very simple. We've been looking into 3D printing prototype of the kit, but due to time constraints, we don't have it.
So did you put together maybe a prototype kit in terms of just having it in wells and you just didn't make the plate? Like, can you elaborate a little bit on what you actually were able to produce as your prototype kit?
Yeah, so our experiments were performed in 96 well plates in which we just directly added our cell line. So it will be similar in function to the final system, just so that's the main difference is that we didn't freeze-dry them in advance, but we just added them directly from our cultures into 96 well plates for testing.
Okay, thank you. Okay, if there are no further questions from the judges, we have one in the audience. We have some more time. Please introduce yourself and then...
Hi, my name is Bastien Thiel from the Netherlands, also. So it sounds really good to decrease indeed the amount of antibiotics released in the environment. But I'm wondering whether you have any expectation, since you mentioned that like decreasing or like using combinations of stressors and antibiotics would decrease the development of resistance. But why do you expect that? I mean, why wouldn't there be resistance going just as fast as with only antibiotics?
Yeah, well, so the main reason we believe that was, showed in the slide before, is that because a combination of stressful compounds can be used to target multiple different cellular pathways. So the bacteria can't just become resistant by, for example, overcoming ribosomal stress, because there will still be substances targeting the DNA or the plasma membrane, and thereby, well, it will hopefully slow the formation of resistance.
Okay, so do you know that these things indeed target different pathways?
Well, we've currently not developed a combination therapy of stressful substances yet, but the goal would be to develop a combination which does.
In the back.
Thank you very much. So Chris Core from the University of Warwick. So how easily could you transfer your technology to other bacterial pathogens?
So your question is how we could use other model organisms than E. coli, right?
Other escape pathogen, for instance, yeah?
It would be vital to use a promoter repertoire that is indigenous to that particular pathogenic strain. So if you were to use another, you would have to isolate other promoters and integrate with that using the culture test. So different from E. coli.
And we've already identified some promoters in Bacillus, for example, so to both have a system in gram-negative and gram-positive, but due to time constraints we weren't able to finish our system in Bacillus subtilis.
Okay, I think with that we're going to end the session. Thank you so much again, Team Leiden. Give a big hand of applause.